parallel operation of transformer. Yesterday we have seen that what is the necessity of the parallel operation and the condition for connecting two or more number of transformer in parallel. That is connecting two or more number of transformer, that is a primary winding across the source bus, and the secondary side is connected to the load bus. The reasons for connecting the two transformers in parallel were listed out yesterday. That is non-availability of the bigger size transformer to meet the need of the larger load. Then as the demand increases, it is not possible to replace the existing one. Instead of that, we have to use a smaller units. They are connected in parallel. As and when there is an increase in the load, we can go on adding the smaller units in the parallel. That is another advantage of connecting the parallel connection of the transformer. To ensure the improved reliability, that is, if you are using only one transformer for the catering needs of the load, then if there is anything happens to the transformer, the whole of the load is set down. Okay. For that purpose, if you are using a smaller number of units in parallel, then in any one of the transformer goes out of order, the standby unit can be switched on and the total supply can be continued. To reduce the spare capacity, that is standby unit cost is reducing if the smaller units they are connected in a parallel, and the transportation problem for the bigger unit of the transformer, also there is a problem with the installation. Therefore we are going for the parallel operation of the transformer. Then the condition for connecting two or more number of transformers were listed, that is the voltage ratio must be same, and the per unit impedance of each machine on its own base must be the same, and the polarity must be the same, and the reactance per resistance ratio, that is reactance per reactance by resistance ratio of the transformer should be the same. These are the four conditions to be fulfilled to connect the transformers in parallel. Okay. Now we will see how the transformers they are sharing the load if they are connected in parallel. That is, we are seeing there are two transformers who are marked with their polarity and they are connected to the supply bus, the primary, and secondary is connected to the load bus. In the load bus, we are connecting a load. The induced voltage in the primaries are E1 and E1 and E2 and E2, and here what I am calling here is load is connected across the two load buses, okay. Then the current supplied by the individual transformer is I and the IB. Then we will see how actually the load is shared between the two transformers when they are equal voltage ratio. They have got a equal voltage ratio. That is, you are taking here two cases. One is equal ratio, another one is unequal ratio. First, we will take equal ratio. Always two transformers of equal voltage ratio are selected for working in parallel because we are not giving any scope for circulating current which is flowing between the transformer. This way one can avoid the circulating current between the transformers, and load can be switched on subsequently to the bus and neglecting the parallel branch of the equivalent circuit can be shown as in the figure. That is what I am doing. I am connecting the two transformers in parallel. The transformer is represented by its equivalent circuit diagram. However, you are neglecting here the parallel branch component of R0 and X0. The same thing is written here, neglecting the parallel branch of the equivalent circuit can be shown as shown in the subsequent figure. The equivalent circuit is drawn in terms of secondary parameters because the load is connected across the secondary of the transformer. The equivalent circuit which is shown as referred to the secondary side. This may be further simplified in the step by step so that we can find out what is the current shared by the first transformer and the second transformer. The voltage drop across the two transformers must be the same by virtue of common connection in the input as well as output, and it's quite evident because both the transformer are connected to the same supply and it is connected across the same load bus. Therefore, the voltage drop across the two transformers must be the same. Okay. Now I am tilting the circuit diagram which is drawn previously. Here we have got a supply bus, we have got a load bus, and the two transformers they are connected in parallel with their induced voltage in the primary as well as the secondary, and the current delivered by the individual transformer as IA and IB. Now this whole circuit diagram can be replaced by a equivalent circuit diagram. The whole transformer can be represented by its equivalent resistance and reactance referred to the secondary side. Similarly, this transformer is also replaced by its resistance and reactance referred to the secondary side, and the load is connected. Just we will see how exactly work. That is, this transformer is replaced by, we have got two buses, that is a supply bus and the load bus. I will draw as it is here. This is a supply bus, that is a load bus, and instead of all this structure is represented with a circuit diagram, I am representing this by its equivalent circuit diagram. We have drawn already. It is consists of resistance and reactance. I will start with the transformer A, that is I am representing connecting from bus to what is that? The supply bus to the load bus with RA and XA, that is the total impedance of the one of the transformer, that is ZA transformer is ZA. Then the current delivered is IA, that is connected in. You are started here, therefore I am connecting to this bus, therefore I am starting here at this bus. Okay, then from here to here it is connected to the second bus, therefore RA which is connected here. And the other end you can see here, other end, that is the return path is from here to here. Just I am representing by line here. From here to here, you can see here, from here to here. This is a you are replaced this whole circuit by its equivalent circuit diagram here. Similarly, we can replace this by its equivalent circuit diagram. That is, you can see here from once again here to here, that is from here to here, that is started with this line. Therefore, I am started with this line and ending with the load bus of this, ending with this. The current delivered is IA. Then the return path is from here to here. Therefore, I am connecting from here to here. These are the two transformer is represented by its equivalent diagram. You can see here it is connected between this and this bus. This also connected between these two, this bus. Then this return path is also connected between these two. Means this and this they are parallel. This and this are in parallel. Therefore, you can draw redraw the circuit, simplify the circuit diagram. What I am doing here is, see here, I am taking RAXA and RBXP. They are connected across the same terminals, therefore they can be connected in parallel. Therefore, I am shorting here. Supply bus I am drawn, load bus. Then you can see here I am shorted here and connected between this bus to this bus because these two are connected in parallel. Similarly, I can replace these two lines by a single line that is connected between this point to this point. This is how we are modified this circuit diagram to this simplified circuit diagram. Now, I have got the two branches, they are connected in the parallel. Therefore, further what I am doing, further I am reducing the circuit, like I am connecting from here. I am connecting a source. Source is replaced by now a source here, and here it is connected load. Therefore, between these two, I am connecting the load. Means across this there is a load is connected here in between, and this whole circuit can be replaced by RA and XA, RB and XB. They are connected in parallel. Then it is connected to source. The source is replaced by a source. It is a symbolic representation of a source. Then here we are connecting a load that is represented by this load. Then we know that the current which is delivered by the transformer is I, and the current delivered by the transformer B is IB. The same thing I am taken here. Here also it is IA and IB, and the current which is flowing through this is sum of IA and sum of IB. That is IA plus IB gives the total load current. Therefore, IL is equal to, it's a vector sum of IA plus IB. Means this whole circuit diagram can be represented by its equivalent circuit diagram by parallel connection reduction. Just I am drawing a simple circuit for the two transformers. They are connected in a parallel with a source and a load with its the resistance and reactance in the secondary side. This is a figure what I am getting. From this, we will find out what is the load shared by the transformer 1 and 2 or A and B. Just I will redraw the same thing here, that is source here, that is E2, because I am referring this transformer drawn refer to the secondary, therefore source available across the secondary is E2, then the voltage which is available across the load is Vn, the current delivered is IL, therefore the total current, that is the current delivered by A is I, and from the transformer B it is IB. Sum of these two current, that is a vector sum of these two current, gives the I. Therefore, you can see this parallel branch and the voltage across these two is the same that I am representing by V, and the parallel combination impedance what I am representing is Z. That is, the whole thing can be reduced to a single resistance and single reactance, or single impedance consists of resistance and reactance. Okay. Same thing I have written here. That is IAZA. That is IAZA is the voltage. That is V is nothing but I into ZA. That is also is equal to IB into ZB. IB into ZB. Sum, that is a product of IB and ZB is also V. Product of IA and ZA is also V. Therefore, because they are connected in parallel, therefore I call as say V. That is, if we are replacing by a single resistance reactance, then it is become I into Z. What is I? I is the sum of IA plus IB. IA plus IB gives I. Therefore, IA plus IB is equal to I. And Z is the equivalent impedance of the two transformer given by. That is how we are calculating the equivalent impedance if they are connected in parallel, just like a resistor. That is 1 by R1 plus 1 by R2. That is R1 R2 divided by R1 plus R2. Similarly, here Z is equal to ZA plus ZB divided by ZA ZB is the equivalent impedance of this parallel combination. Okay. Then we can see how we are finding out the current I. I can be calculated by it is V by ZA, because the voltage across the parallel combination we know, that is V is equal to I into Z, or it is IAZA or IBZB. That is nothing but it is V divided by ZA. V, that is the voltage across the branch A is V and impedance is ZA, therefore V by ZA. What is the V? V is nothing but I into Z. Therefore, I into Z divided by ZA. Z is nothing but ZA plus ZB divided by ZA plus ZB. That can be substituted in this equation. That is Z by ZA. That is ZA ZB divided by ZA plus ZB. Okay. That is something it is, and Z is equivalent 1 by R1 plus 1 by R2, that is R1 R2, that is, it is a reciprocal, you have to get it here. You have to get here. That is, it is actually that is 1 by Z, 1 by Z, where Z is equal to, it is ZA ZB divided by ZA ZA divided by ZA plus ZB, ZA plus ZB, that you have to make it. Okay, that is a mistake, it is 1 by Z there. Okay, then if you are substituting the value of Z here, that is to replace the Z by ZA ZB, because you take the reciprocal of this, that is what I am getting here is ZA ZB divided by ZA plus ZB divided by ZB as it is. Therefore, after substituting and this ZA get cancelled, then IA is given by I into ZB divided by ZA plus ZB. Okay. Similarly, you can go for the IB. IB is once again it is V by ZB. However, V is equal to I into Z. Then once again you substitute the value of Z. Z is ZA plus ZB divided by ZA plus ZB. Then once again ZB get cancelled. Then IB what I am getting is I into ZA plus ZB. That is, it is nothing but it is a parallel branch combination. That is, a current in the one branch is equal to total current multiplied by impedance in the other circuit divided by total impedance. Similarly here, the current IB is equal to total current multiplied by the impedance of the other circuit divided by sum of the impedance. Okay, this is the current which is delivered by the transformer A and transformer B. Then we can observe here there is one statement I made here, that is, if the terminal voltage is V is equal to I into ZL, then the active and reactive power supplied by each of the two transformers is given by. How we are finding out the reactive and active power delivered by the transformer A and B? That is, it is a product of real part of the VL into I is gives the active power, VL into IA of the active power, that is the terminal voltage VL multiplied by active component of IA gives the power delivered by the A. Similarly, the real part of VLIB gives the active power delivered by the transformer B. Similarly, the reactive power which is delivered by the transformer A is imaginary part of VL into IA. Similarly, the KVA delivered by the KVAR delivered by the transformer B is imaginary part of VL into IB. From the above, it is seen that the transformer with higher impedance supply the lesser load. You can see here, impedance with the higher impedance. Suppose ZA is higher. ZA is higher. If the ZA is higher, in that case, it is seen that the transformer with higher impedance supplies lesser load, has got lesser load, and vice versa. If it has got a higher impedance and it is delivered the lesser, because ZB is less than ZA, therefore IA is delivered lesser current. This is how we have to interpret. Then we will draw the vector diagram for this. That is, first you have to take, that is here, first start with the voltage is E2, that is we have to get E2 from the VL. VL can take as a reference, and first you have to take the voltage V, and thereby it is what we are getting is VL. V and VL is remain the same. We will show you how exactly we are drawing here. That is the terminal voltage across the load, that is V2 or VL. Then IA is the current delivered by the transformer A, which is lagging V2 by an angle of phi. Then IARA, which is drawn parallel to IA. Then it is added to IAXA. Then what I am getting is E. Similarly, you can draw IB, which is lagging phi B, and IBRB, which is drawn parallel to this, and IBXB perpendicular to IARA. Then what we are getting is the total sum of IIB, what I am getting is IL. Then here the ILRL, which is the total load current, it is given by, that is drop, it is ILRL, and ILXL, that also gives the same voltage E. This is how you have to analyze the parallel operation of the transformer with the same voltage ratio. The load shared by a transformer is given by I into ZB, Z plus ZB, IB is equal to I into ZA plus Z.